Hello and welcome to our video on non-homogeneous Sturm-Liouville boundary value problems. These are boundary value problems of the following form. The differential equation part is given by first derivative on the product p of x times f prime plus q of x times f equals lambda times r of x times f plus h of x over the interval a to b, where p, q, r, and now h are given functions, lambda is a given real number, and f is the desired unknown, coupled with the two boundary conditions, alpha 0 times f of a plus alpha 1 times f prime of a equals 0, and beta 0 times f of b plus beta 1 times f prime of b equals 0. Here, as before, p is continuously differentiable and positive, and q, r, and h are all continuous, and r is positive. We assume, as before, that not both of alpha 0 and alpha 1 are 0, and not both of beta 0 and beta 1 are 0. Our goal is to find a function f solving this problem, as well as the parameters lambda that might work. Why do we call this a non-homogeneous problem? Well, it's just a non-homogeneous ODE. If you subtract the lambda r of x f term, you get first derivative on the product p of x f prime plus q of x f minus lambda r of x f equal to h of x, and that left-hand side is certainly a nice differential operator, so it's a non-homogeneous problem. We recall some notation. We put SR on f is 1 divided by r of x times the first derivative on the product p of x f prime plus q of x on f. And in this case, the ODE is equivalent to SR on f equals lambda f plus h divided by r. We know a lot about this operator SR. It has a countably infinite family of eigenvalues, lambda k. It has simple eigenfunctions phi k, which is to say that SR on phi k equals lambda k times phi k. And we know we can write any function g that's continuously differentiable on the interval a to b as a sum of these eigenfunctions. Namely, g of x is the sum from k equals 1 to infinity of theta k times phi k of x over the open interval a to b. There might be some problems at the endpoints a and b, where here theta k is 1 divided by the L2R norm of phi k squared times the inner product of g with phi k in the L2R norm. So for the purposes of solving this boundary value problem, let's also assume that our given functions r and h are continuously differentiable on the interval a to b, not just continuous. And in this case, we can write h of x divided by r of x. That's going to be a continuously differentiable function because r is never 0. So we can write h of x over r of x as an eigenseries of the form sum k equals 1 to infinity, theta k times phi k of x, with a formula for theta k if we really need it. Specifically, we have theta k equals the inner product of h against phi k in the plane L2 norm divided by the L2R norm of phi k squared. Why do we have only the plane L2 norm of h against phi k here in the numerator, not the L2R norm, as I said a moment ago with g? Well, what's the inner product of h divided by r against phi k in the L2R norm? I'll leave you to calculate that yourself, but the r's cancel out. Now here's the idea going forward. We want to find a solution to this boundary value problem, f, and if we can, we expect that we can write f as an eigenseries, namely f of x is going to be the sum from k equals 1 to infinity of mu k times phi k of x. Our job is to find the coefficients mu k. We'll assume that we have a solution, f, to the boundary value problem. We'll assume that we can write f as the eigenseries with coefficients mu k, And then we're going to try to find formulas for mu k. So as we often like to do, we work backwards. Now, what do we want in this problem? It's rephrased as SR on F minus lambda F equals H over R, where we know everything there could be to know about H over R. We know what SR does. So let's expand both sides as series in phi k. That is to say, we want SR on the sum from k equals 1 to infinity of mu k phi k, where the mu k's are unknown, minus lambda times the sum from k equals 1 to infinity of mu k phi k, equals the sum from k equals 1 to infinity of theta k phi k, where now the theta k's are known to us. They're given to us by H and R. And remember, of course, that phi k's aren't scalars, phi k's are functions here. So let's play around with these series and see what this teaches us. Well, assume that I can move my operator SR inside the infinite series. That's kind of a big assumption because it's an infinite series here and not just a finite sum, but it stands to reason. SR is a linear operator. It should commute with series. So if it does, I have the sum from k equals 1 to infinity of mu k times SR on phi k minus, I move the lambda inside the sum from k equals 1 to infinity lambda mu k phi k equals sum from k equals 1 to infinity theta k phi k. Okay, what does SR do? SR on phi k, well, this is an eigenvector relation. So now I have the sum from k equals 1 to infinity mu k lambda k phi k, because SR on phi k equals lambda k times phi k. And then the other two sums remain the same. So let me combine the two sums on the left-hand side now as the sum from k equals 1 to infinity mu k times lambda k minus lambda times phi k equals the sum from k equals 1 to infinity of theta k times phi k. I'll bring the sum on the right side over to the left. So it's now my sum from k equals 1 to infinity mu k lambda k minus lambda phi k minus sum k equals 1 to infinity theta k phi k equals 0. And I will combine all those sums together. Sum k equals 1 to infinity mu k times lambda k minus lambda minus theta k times phi k equals 0. Okay, a lot of sums here. The only dicey thing that I did, I think, was interchanging the infinite sum and the SR operator. Other than that, this was all just algebra of infinite series. I'd like to say that having the sum from k equals 1 to infinity of mu k times lambda k minus lambda minus theta k times phi k equals 0, that forces each of these coefficients, mu k times lambda k minus lambda minus theta k, to be 0. Because in that case, I could pretty easily solve for mu k. So does that work out? Well, yes. Remember, the phi k's are all L2R orthogonal. Namely, the inner product of phi k with phi j with respect to L2R is 0 whenever k is not equal to j. So what does this say? Suppose you have a sum of the form sum k equals 1 to infinity theta k phi k equals 0. Well, that just means that the inner product of this sum from k equals 1 to infinity with a given phi j has to be 0. And then assuming I can pull that sum out of the inner product, which I should be able to do, I get the sum from k equals 1 to infinity of theta k phi k against phi j equals 0. And then I pull that theta k out of the inner product using algebraic properties of the inner product. So I have sum from k equals 1 to infinity of theta k times the inner product of phi k with phi j equals 0. But I know these inner products of phi k with phi j, they're all 0 except in one special case. Namely, in the case that k equals j. So this tells me that theta j times the L2R norm of phi j squared is equal to 0. But phi j is a non-trivial function. from what I've been assuming all along. So its L2R norm is not going to be 0. So if I have the product, theta j times L2R norm of phi j squared equals 0, that can only happen if theta j is equal to 0. Going back to our previous slide, this kind of orthogonality argument shows that, happily, mu k times lambda k minus theta k is equal to 0 for all k. And again, remember, we know from the start of the problem what lambda k and theta k are. So if lambda k is not equal to our given parameter lambda for all k, then we can happily solve for mu k as mu k equals theta k over lambda k minus lambda. And we conclude then that the formal solution to our boundary value problem is f of x equals the sum from k equals 1 to infinity of theta k over lambda k minus lambda times phi k of x. And just to be clear, we know what all the data is in this series. The eigenpairs of the boundary value problem are the scalar lambda k and the function phi k. We're assuming that lambda k is not equal to lambda for all k, and we're assuming that we have the representation h over r is the sum from k equals 1 to infinity of theta k times phi k. So if you have all this, then at least formally, the solution to the boundary value problem is given by this very particular eigenseries. And then you would have to do some more math to check and make sure the solution converges and that it's actually differentiable. Or you could use this series to approximate the solution to f and truncate the series not at full infinity, but at some finite upper index. So now we should ask ourselves, what happens if lambda is equal to lambda j for some integer j? What happens if the lambda parameter in the boundary value problem is actually equal to one of the eigenvalues? Can we do anything in this case? So if we go back a little bit, let's look and see at all the work we did. Where did it start to matter that lambda would not be equal to lambda j? How did we do all this? We assumed we had a solution to the boundary value problem of the form sum k equals 1 to infinity mu k times phi k. We found that forced the relation mu k times lambda k minus theta k equals 0, where we know what lambda k and we know what theta k are. And if we take k equal to j, what is this force? We need to have theta j equal to 0. So let's go back a little bit. Theta j is the inner product of h against phi j in L2 divided by the L2R norm squared of phi j. So if theta j is equal to 0, that means that the inner product of h against phi j in L2 is equal to 0. So what do we conclude from this formal analysis? If lambda is equal to lambda j for some j, if the scalar parameter lambda is one of the eigenvalues of the boundary value problem, then in order for the nonhomogeneous boundary value problem to have a solution with the nonhomogeneity h, we need the inner product of h against phi j in L2 to be equal to 0. We need the inner product of h against the corresponding eigenfunction phi j to be equal to 0. This is a solvability condition for our problem. It tells us that if the solvability condition is not met, if the inner product of h against phi j is not 0, then we cannot solve the nonhomogeneous problem. But suppose we do have the solvability condition met. Suppose we do have the inner product of h against phi j in L2 equal to 0. Then it turns out we can still solve for f as this eigenseries sum k equals 1 to infinity of mu k against phi k as before. We can determine all of the mu k's uniquely except for mu j. Here's what we obtain. F of x is now going to be the sum from k equals 1 to infinity, excluding k equals j, of theta k divided by lambda k minus lambda phi k of x. This first sum excluding k equals j are all of those mu k's that we could determine uniquely, plus a constant c times phi j of x, where now c is an arbitrary constant. In other words, if the solvability condition is met when the parameter is equal to an eigenvalue, then the boundary value problem has infinitely many solutions. So we see three possible behaviors for a boundary value problem. It could have a unique solution, it could have no solutions, it could have infinitely many solutions. And certainly this is a far departure from what we knew about ordinary differential equations and initial value problems.